u substitution, where we pick u to be something complicated in the integral, and then we deal with the consequences from that. So the idea is there's something we want to cover up or get rid of, and that will be the most complicated thing that we can still have present a derivative for in the integrand. So number one's very easy, just like the examples we did in class on Wednesday. U is that stuff in the bottom radical, and the du is exactly right there. So when you transform the integral, you might even rewrite it as u to the minus half du before performing the antiderivative, which is bump it up a power and divide, right? So u to the minus half becomes u to the positive half. Multiply it by 2. And then the very last step is to return to x where we came from. This thing has to go inside there. So the antiderivative is really 2 times x squared minus 1 to the positive half plus c. Okay. Any questions on the basic example? Okay. In number 2, sine and cosine are both derivatives of each other. So you might be tempted to pick a u here and have a du here, or this could be u and that could be du, but it will only work if we pick u to be the more complicated thing. The differential, like this dx in both cases, or any of the du's, needs to be, let's just like a free little tag-on thing at the end of the integral, so that du can't be squared, it can't be inside anything. The du just has to be like, just right there, very small, lonely. Nothing interesting happens to du. So pick u to be the complicated thing always. It will only work if we let u be cosine. And then the derivative of cosine is du, which is negative sine x dx. Remember that differential dx because that's part of the integrand, and we want to make sure that they get exchanged. Like all the x's have to come out and all the u's have to go in, so the dx goes inside the du. Ashley?
Can you still do negative du equals sine x dx?
Yeah, so just like we saw on Wednesday, or no, today's Wednesday, like we saw on Monday, the u is in the denominator and the du's almost match, but what we have in the integrand is sine and the du we have is a negative of those. So it's not a bad thing or perfectly fine to say that this is worth a negative version of the differential du. Make sense? We just adjusted it so it matched in the integrand. Then we find the antiderivative. Tate, what's the antiderivative of the du over u? Natural log of the absolute value of u, and the negative is okay, he can just go out there. It's just a constant, like a times a negative 1, or if it was a 5, you would just have a 5 there, right? And then the last step is to replace, return back to x, the natural log of the absolute value of cosine plus c. Make sense? So you probably didn't notice, and it wasn't too cruel to you to give this to you as what it really is, but this is the antiderivative of tangent, right? Isn't that what sine over cosine is? So you might see that, or maybe you have to take the antiderivative of cotangent, and the first trick is open it up to sine and cosine so that you can have a u and a du. Make sense? So what about cotangent? Just for discussion purposes, if we had to find the antiderivative of cotangent x, what's cotangent? Cosine over sine. Which one can be u now? Sine, yeah. And then du would be cosine dx. Just for comparison, because they're in other order. So it's not that u can't be sine, it's just that u can't be in the numerator, it has to be in the denominator. So here we saw a little tiny adjustment to the du with a negative sign, and here you have to make another adjustment to the du in number 3. So now that you're kind of practicing these, Joe says they're all different, and that's true. But you're developing techniques for finding your u. Think about things that are inside parentheses, maybe trig functions like we saw before, but most importantly, we need something whose friend is still there, whose derivative buddy is present. So you might think like x to the 4th looks like x to the 3rd, or they would differentiate there. So you need like the thing and its derivative in some form. So that's how you know you picked the right u. Why couldn't we pick sine as the u?
By itself, there's no return function for the derived.
Right, there's no du, so you wouldn't be able to make the exchange. Deal? All right, so in this case, we let u be 2x to the 4th, and then the derivative of u, like, this is the thing that came from there, and we don't look at that anymore. We just take the derivative of u, which is 8x cubed dx. And then, after you cook up the derivative of u, that's exactly what it is, then you look over here to see how you can make them match and line up and exchange them. So don't look in the integrand and think like whatever's left over is the du. The du is actually the derivative of u. Make sense? So now we have to make it match. We have 16x cubed dx's, and there's only 8x dx's in my du. This is u, so that's handy. But how can we adjust du to make it match what we have in the integrand?
Multiply by 2.
Multiply by 2, and that's fair, right? This is a standard equation, so if we just operate on the basis of like linear equations, multiply both sides by 2, we find that 2 du's are worth 16x cubes dx's. And this is where the du kind of starts to derail for some people. It's not a single du, but there are 2 of them. We're going to do more of that today. Rewrite the integral. The 16x cubed becomes 2 du. By convention, the du's, the differentials, go at the end of the integral. The sign did not get messed with. You see how it's not our u? That's the function. So it's 2 sines of u. Du. An easier thing to find the antiderivative for, then it's easy from there. The antiderivative sign is cosine. Cosine is negative. U is the argument, and then return it to x. So negative 2 cosines of 2x to the 4th plus c. Make sense? Okay, that's a very basic u substitution.